All right. Good morning, good afternoon, and good evening. Thank you, folks, for joining us for another machine learning community stand up. I am your host, Luis, and with me today is Mark, who's going to be talking to us about SynapseML and doing machine learning at scale. Mark, would you like to introduce yourself?
Yeah, hi everyone. I'm Mark Hamilton. I'm a software engineer here at Microsoft and run the SynapseML distributed machine learning library, and really excited to share some of the things we've been working on with you today.
Awesome. Yeah. But before we get into Mark's talk and his presentation, we're going to talk a little bit about some of the community links and things that are happening around the sort of machine learning, broader machine learning.net space. So let me kind of switch into that and share my screen here. Um, so the way that you can access these is if you go over to aka.ms/mlnet-standup links, and that's going to bring you here to this one page here for today's stream, right? Um, so with that, let me kind of get started. Let me get this out of the way. So one of the things that I kind of want to point you to is this .NET Data Documentation Hub. And basically, this is a landing page inside of Microsoft Docs, which takes you through a variety of different offerings that we have here at Microsoft for working with data. So some of those that you might be familiar with already are things like Link, right? Other things are Azure Cosmos, Entity Framework. ML.NET is there as well for your machine learning needs, as well as .NET for Apache Spark, and we'll hear a little bit more about that and SynapseML throughout Mark's talk. The other thing that I kind of wanted to point you to is this really neat course that was put together by, I guess the account here is Tutorials team. And basically, this is a complete course that goes through machine learning with ML.NET for absolute beginners. So you're going to see here that there's many parts here talking about ML, AI, and just explaining sort of the fundamentals of machine learning, all the way through working with the SDK and building actual experiments for regression and different machine learning tasks. So if that's something that you're interested in, make sure to check it out. It looks like there's about 75 videos here. But yeah, definitely encourage you to check those out. The other thing that I'll sort of point your attention to here is Plotly.net. So Plotly.net, for folks who are not familiar, is this library for building charts and building visualizations utilizing .NET. So this Plotly is a well-known and sort of widely used sort of plotting and charting library, and Plotly.net contains sort of the .NET components that allow you to do that. As it pertains to how we use it today inside of our products in ML.NET, many of the notebooks that we've sort of created currently use Plotly.net. Um, However, the library is built primarily in F sharp, which is great. But when it comes to working with it in C sharp, right? The IntelliSense, there were a few issues with the IntelliSense and stuff like that. So the folks over at in the Plotly.net team, the maintainers, have done a really excellent job here of trying to port over and build sort of a .NET, C sharp bindings for the Plotly.net library. All right. That being said, though, there is a lot to still go through, and while a significant amount of work has been done already, they're looking for help and they're looking for people to contribute. And if this is something that you're interested in, I would definitely um, encourage you to go ahead and check out this issue here, Plotly.net issues 296, which is also in the community links as well. And if there's anything here that interests you, by all means, feel free to go ahead and help these folks out and make sure that the way of using this in C sharp, it just improves and gets better, right? The other thing that I kind of want to point your attention to here, this is over in the .NET Machine Learning repo, so the ML.NET repo, is named entity recognizer. So currently, we are in the process of actively working to bring named entity recognition to ML.NET and being able to allow you to sort of do that natively with our set of libraries and all that, at least for now, is going to be powered by TorchSharp, very similar to the text classification API that we introduced earlier this year or a couple months ago. However, in order to make this a really good experience, we kind of want your feedback. And this thread goes back to 2018. And we're actually actively trying to make this happen. But basically, the thing that I kind of call out and would like your help on is helping us understand what does your data look like and what is your process for getting your data into the right format so you can then feed it to some sort of algorithm or wherever it is that you're doing either training or at the very least performing some sort of inferencing with pre-trained NER type models, right? So helping us understand what your data looks like, and the tools, the processes, all those things that are involved with getting your data into the right format to be able to train custom NER models would be really helpful for us in making that a really smooth sort of experience. And then this kind of just goes into some of the things that Mark's going to be talking about. But there was a blog post, I believe it was last week, that this was published, just talking about in general what SynapseML is, and specifically SynapseML for .NET, which again, Mark's going to talk a little bit more about. If you're interested in reading this blog post, it's in the show notes as well. But you can also visit the dev blogs here and see that. We also included in the show notes the link to the web page, which kind of helps you get started on understanding what are the different ways that you can, what are the different things that you can use inside of SynapseML, as well as, this work is open source. So, if you have any comments or anything like that, issues, pull requests, contributions that you'd like to make, you're certainly able to do that as well. And again, Mark will be talking a little bit more about that, for the next few minutes. So with that, it concludes this portion of the community links, and I'll just go ahead and hand it over to Mark, who's going to talk to us more about SynapseML. Mark, I'll hand it off to you.
Awesome. Thanks so much for the great intro, Luis, and really excited to see all the latest stuff kind of being brought into the .NET community. And we're hopefully going to join that train of folks bringing things into the .NET community, and that's what we'll be talking about today. Is SynapseML, our large-scale open-source distributed machine learning library, which, as of the latest release, has a whole set of bindings for the .NET ecosystem. So C#, F#, and whatever other crazy languages you're using over in the .NET ecosystem. So to get started, what is SynapseML at an incredibly high level? It's an open source machine learning library that's simple. We try to make all the APIs the same and as simple as humanly possible so that you don't have to think too much when you're building your machine learning algorithms. And you can click them together like Lego pieces. Scalable. Everything in the library is naturally scalable. You can run it on your local laptop, or you can run it on large serverless and elastic clusters in the cloud, or on your on-premises machines or your Kubernetes clusters. And open. So, we really want to support a lot of different platforms for running these kinds of things. So Synapse is in the name, and so we can definitely run it on Azure Synapse, but you can run it on Azure Databricks, HD Insight, wherever you get your Spark clusters, and all of the code that I'll be showing today is open source so that you can play with it, you can tinker with it, you can submit PRs, and we really welcome that. Any sort of contributions are always welcome to the SynapseML library. So today I'll give you first a brief overview of what we'll be chatting about. So we'll talk a little bit about the background, what's Apache Spark, what's SparkML, what's Spark.NET, how do these things interact, and what part of the process do they play. Then we'll talk about SynapseML that kind of builds on some of these pieces, and we'll dive into some of its features. So we'll talk about using cognitive services, using deep learning models, using training your own models with LightGBM, and finally explaining the predictions of models, as well as how we're able to support the .NET ecosystem in addition to a variety of other languages. And finally, we'll see a few applications and customer engagements that we've done in the past for the Metropolitan Museum of Art and for Hendrick Motorsports NASCAR racing team. So stay tuned for fun things you can do with SynapseML at the end of this talk. So to kick things off, the core bread and butter that we'll be talking about today is the distributed computing framework Apache Spark. This is kind of the foundational layer of SynapseML, and it's what we build on, and what a lot of other folks in the community build on to reach very large scales. And so what is Apache Spark? It's a distributed computing framework that combines elements of SQL, so think tables, columns, selects, wheres, and joins, with MapReduce. So this is kind of the Google style of parallelism, where you have a whole bunch of data and you phrase a distributed computation as a sequence of maps on this data. And you can also reduce the data. So if you're doing something like a word count, you might want to map a document to a list of word counts and then combine these word counts to get a global word count across all your different documents. Um, what's nice about Spark is that it's elastically scalable and fault tolerant. So the clusters can resize depending on the actual workload that you're running, to either scale out to actually support all of this and get it done as fast as possible, or if you're not using machines, to scale down and save you some money. And part of this generality is that you get fault tolerance. If one machine fails, oh well, it's like you shut down the machine. Same kind of thing. And finally, Apache Spark is written in Scala, an object-oriented and functional programming language, much like F Sharp, but on the JVM. And it's got bindings in a variety of other languages. So you get Java for free because it's in Scala, but you also get the R, Python, Julia, .NET, C Sharp, F Sharp. And there's probably more too these days. So a lot of people have built out these bindings for Apache Spark so that you can work with Apache Spark and command these Apache Spark clusters in whatever language you please. And in terms of the fundamentals of what Apache Spark kind of looks like, over here on the right, you sort of see an architecture diagram that the cluster is composed of a driver node that kind of keeps everything running. This is the central orchestrator. And it's composed of many workers. These are these fault-tolerant machines that get spun up and spun down as needed. And these workers directly connect to data in the form of local files, databases, Kafka clusters, Elasticsearch clusters, cloud storage, really you name it. There's hundreds of different connectors for Apache Spark, and you can kind of connect to data wherever you particularly have it. And these workers will connect in parallel and suck the data out, process it, and either give you results on the driver node or write your results somewhere else in another database. So that's kind of roughly how Apache Spark works. Um, in terms of where you can actually get Spark these days, that there's a few options for Spark as a service if you're working on the cloud. So Synapse Analytics is Microsoft's first-party managed option. Likewise, Azure Databricks is a first-party managed option on Azure. There's also Databricks on AWS and GCP. HD Insight, this is sort of a bit older, the first party option for Microsoft, and it's a bit less managed. You know, you're going to be tuning and twiddling dials a little bit more than you would be in Synapse. And you can also roll your own if you have Spark on Kubernetes or something like this. So if you've got a big Kubernetes cluster that you manage, you can throw that up there. We have a Helm chart, and also the Apache Spark project has a set of Kubernetes operators that allow you to run Spark on your Kubernetes cluster. And you can also run this locally on your laptop as well. So now that we've kind of seen Spark and we've seen where to get Spark, the next step in building SynapseML is .NET for Apache Spark. So this is the particular .NET language bindings for Apache Spark. And they're nice and they're idiomatic. So if you're in C# or F#, you can use Apache Spark using these .NET bindings. And it sort of looks like all of the other language bindings in that you have Spark Core sort of at the center, written in Scala, and then you've got an interop layer between Scala and the C#, F# side in the .NET ecosystem. And so what it kind of looks like to work in Spark is like this code sample on the right here. You can read in input data. You can use selects and sort of the SQL statements in order to process your data, apply functions like splitting words based on spaces. You can do various different kinds of table operations like exploding, group bys, counting. And this is a very quick example of what it would be like to write a distributed word count application in .NET for Apache Spark. And what's more is that the .NET for Apache Spark doesn't just allow you to control kind of key Spark SQL operations. It also allows you to inject .NET code into Spark. So in your maps and in your reduces, you can run .NET code like ML.NET models. You can use the entire .NET ecosystem through this .NET for Apache Spark connection as well. So it not only allows you to use Spark in .NET, it allows you to use .NET and Spark, which is really nice. So this is kind of the next step is that now that we have our Spark, we've got it in .NET. Now we want to start doing machine learning. And the core machine learning library for Apache Spark is called SparkML. And what it is it's a high-level library for distributed machine learning. It's inspired by scikit-learn. So here I've shown a little code snippet where you create a model, you can fit that model to a distributed data frame, and then that fitting process returns a fit model here called model. And then you can use that to transform your testing data. So you can take that fit model and you can use it to get predictions out. And what's nice about what's nice about SparkML is that everything has the same API and interface. So everything kind of looks like something that either gets fit on data or something that transforms data. And that makes it really easy to swap out components of your experiment. You know, if you want to take this logistic regression and swap in a gradient boosted tree framework, then it's very easy. Just change that new logistic regression to new like GBM classifier or something like this. And there's also a nice API for composing these machine learning models into pipelines, so that you can take multiple machine learning components and abstract them away into a much larger compositional machine learning component that you can move around and apply to new data sets as you see fit.
There's
So
a few
this is,
questions here, Mark, before
yeah.
you go on that might be related to sort of the .NET components. This first one here comes from Sharafuddin, who asks, like in Python, is there built-in functions to call named entities, which can accept input of text file data?
Yeah, that's a great question. So in terms of these built-in functions that you kind of see here, like split and explode, these particular functions will be sort of your low-level operations, your standard operations. And we'll see in a little bit where kind of applying named entities might come in. So we provide several SparkML transformers that have kind of the API like this that do named entity recognition and other kinds of operations. Likewise, you can also take ML.NET named entity recognizers and apply them here with a user-defined function, or UDF. So that's kind of the way in Spark for you to take .NET code and inject it into your Spark pipeline. So if you have a named entity recognizer, you can also apply it kind of like the split function, so long as you wrap it in a user-defined function. So hopefully that will give you kind of a rough overview of the different ways you can put named entity recognition into the stack here. And so we'll be talking mostly about the SparkML transformer side of the stack. And I think you said that it doesn't work in natural languages, and we build on the cognitive services, as we'll see later in the talk. And the cognitive services support a wide variety of different languages. So hopefully any of the languages that you care about are supported in the cognitive services. So I think Arabic and English are definitely supported, as well as probably like 30 or 40 others.
Yep. Yeah, thanks for that. Few also ask here, when it comes to the data frames, are they type safe?
So I'm not quite sure about whether the .NET team has the Spark.NET team has built the type safe version of the data frame, but in the Scala side, that's sort of where I'm more familiar. There is a nice type safe version called the data set, and you can work with things directly. You get the types flow through the computation. Ordinarily, the data set is filled with rows, and these are sort of a more untyped operation. So these rows contain columns, and you access these columns via string name. So that's sort of the two APIs for the SparkML data frame here. That's kind of the data variable here that you see in the little code snippet. And we can share some links after the talk too to give you pointers to sort of the typed and untyped APIs in Scala, and see if there's a corresponding version in .NET.
Yeah, that would be great. And then I guess last but not least here, before we move on, I don't know if you're going to cover this later on in your talk, but Phil was asking, how do you build the data pipelines? Is it using Airflow, Luigi? Um,
Yeah, so that's a great question. In terms of what we do here in this talk, we mainly just use Spark. That you can do pretty much anything in Spark. You can load from your basic data source, and then apply whatever operations you want in any language you want. So We haven't really yet found the need to kind of move to other frameworks to do pipelining and do operations. Um, we mainly just do everything in Spark here. But that being said, I'm sure that they might have nice integrations with these other kinds of tools. And it seems like Luigi is a tool to coordinate multiple Spark jobs. And that I think you might still be able to apply whether you're using SynapseML or whether you're using just regular old vanilla Spark operations. I think you'd still probably be able to use these tools to coordinate multiple Spark jobs, if you please. But I personally don't use those tools.
Gotcha. And I believe that the answer to this is yes, right? That the .NET for
Yes.
Apache Spark supports Delta Lake.
Yep.
Cool. Awesome. Okay. Well, yeah, keep the questions coming, folks. But in the meantime, Mark, would you like to continue?
Yeah. So this is kind of where we transition to now that we've seen the background of what's Apache Spark, what's Spark.NET, what's SparkML. This is kind of where SynapseML comes in. And what SynapseML does is it takes SparkML, this really nice API for machine learning on Spark, and it scales it out and it brings in a whole bunch of new functionalities into this API. So we had all sorts of new tools for doing gradient boosted trees, for doing cognitive services, for doing responsible AI, open AI language modeling, anomaly detection, all sorts of different new functionalities we've embedded into to SparkML and given SparkML sort of new superpowers in order to solve any kind of problem that you throw at it. And really, our aim is to expand the SparkML API into as many different domains as possible so that you can solve your problem without ever leaving it. And you can have really nice, clean pipelines with very small amount of code that do a lot and really can solve problems in a variety of different domains. And to actually do this, what we've done is that a lot of times that we take various different machine learning ecosystems and we integrate them with the Apache Spark distributed computing framework. So we take things like OpenCV or the cognitive services or Azure Search, and we bring them in and give them really nice Spark idiomatic operations so that you can use these at Spark scale. We won't have time to cover everything today, and we'll hopefully give you a tour of some of the most salient features through what I call the 4 steps of data science. And this is a patent pending method that if you've worked in data science, you might be familiar with. So step one, whenever you get a new problem, is to first ask, please God, hopefully someone's already solved this, that I don't want to actually have to think. I don't want to have to write code. I don't want to have to work hard to solve this problem. Hopefully the problem I've just been given or just discovered is a solved problem. And hopefully it's solved by a service so that I don't even need to maintain anything. And if that fails, if you can't find a service that exactly solves your problem, the next question is there's got to be something pre-trained lying around. Like the machine learning community is very large. Someone's probably solved this and created a pre-trained model for me. So, that's step two. If you can't find it as a service, maybe there's something pre-trained that you can use. And step three is if you really can't solve your problem with one or two, well, it looks like you got to get your hands dirty and train a model. Um, so that's step three is how you actually train a model yourself if you don't have one. And step four is whether you've gotten your model from steps 1, 2, or 3. There's always this lingering question after you've built it of what in God's name is this doing? What is this model predicting? Is this model predicting the right thing? Is this model fair? Is this model correct? Is this model going to get me sued? These kinds of natural questions sort of follow once you actually have this model. And there's also sort of step 5, which is deploying this to production, but we don't have time to talk about that here today. But there's a nice ML flow integration that you can use to do these kinds of things that I'll just briefly mention now. But we'll go through steps 1 through 4 in today's talk. And so we'll start off with step 1. And this is really the aim is to kind of find something that solves the problem for you. And thankfully, Microsoft has come up with a whole bunch of things that solve problems, really hard problems for you automatically. And these are the suite of intelligent services. So things like cognitive services, Bing, OpenAI, Azure ML. And the idea is that these things are pre-built and smart and ready to go. They solve a wide variety of general purpose intelligence tasks, and they're really smart. I mean, I used to work on one of these teams, and they work you hard, and they really care about getting the next few percentage points of accuracy in the state of the art. So you can rest assured that these things are going to be always updating and always improving in performance over time. Um, and one of the beautiful things is that you don't need to train anything, you don't need to deploy anything, you don't need to manage anything. It's just all abstracted away for you, so that you can just focus on solving your problem. And what we've done is that we've taken these intelligent services and we've brought them into the Apache Spark ecosystem so that they now work with massive data sets in your particular database of choice. So they work right where your data is, so that you can apply these things at very, very large scales without having to worry too much about how to actually do that. Um, So I'll briefly show a quick example of kind of using one of these cognitive service transformers, and you'll see that it looks just like all the rest of SparkML. So the idea here is that we have a data frame here that's got a single column called audio. That's our input data frame. And we create a speech-to-text transformer, just like logistic regression model here. And we set a few parameters. We pointed at that column of calls here in our storage account. We say that we want an output column called text, and we say that we're transcribing English calls. And we apply this to our data frame, and we magically get another column appended to our data frame that has the actual text from all these various different calls. And this kind of uses the full distributed nature of the cluster so that it's really fast, it's really simple. And this is now just a new data frame that you can keep working with in your pipeline. You can run named entity recognition on this. You can run it through other things. You can save it out. You can write it to a storage account. You can write it to a search engine. The world is your oyster here. And so, I've briefly showed an example for uh, speech to text, but there's a whole variety of cognitive services we support, over 50 of them. A lot of these are new in the past year. So if you've already looked at SynapseML and you couldn't find what you were looking for, potentially we've solved this in the last year, and we're always adding more of these. So if you have any particular requests for things to add, we'll be happy to add these in. And I'll briefly call out some of the amazing developers that made this possible. So Serena Iran, she's going to be mentioned throughout this talk. She's the one who made the .NET bindings and made a ton of cognitive service integrations like translation and form recognition and multivariate anomaly detection. I mean, she's just prolific and fantastic in every aspect. Wenqing is on our team, and he's been working on making these cognitive service integrations work flawlessly on Synapse Analytics and work in data exfiltration protection mode. Sudhindra contributed our Azure Maps integration. The Text Analytics Explorer interns added healthcare analytics and a variety of other natural language processing capabilities. And Mark Niehaus helped us onboard OpenAI so that you can use these billion parameter language models directly from within your Spark clusters. So yeah, I just want to call out some of these fantastic developers. This is like not the full list of people who have contributed these kinds of things, but some of my favorites. So we've kind of seen.
Mark, sorry to cut you off there. Before we move on, I just wanted to clarify something. We have a question from Sharafuddin here. Can this work standalone without having internet or access to the Microsoft Azure cloud?
Yeah, that's a great question. So the simplest way to set this up is to actually contact the Azure cloud. That for these cognitive service integrations where you're looking for a service to solve your problem, the simplest way is to contact the cloud. That being said, the rest of this talk will focus on things that are sort of offline capable. And there's also a way to take cognitive services and run them in containers. So you can run a little cognitive service deployment locally and contact that instead of the cloud so that you can work without the internet or outside of the cloud. And this is particularly useful if you deploy these things on Kubernetes. You can have your containers over on one side of your cluster and your Spark cluster over on another side, and they can talk to each other and independently scale out to fill your need. And you can also run the container kind of locally on your computer as well and call into that. And this can also help you adaptively scale this and make this even more efficient because you don't even have the latency of going up to the cloud. We won't have time to talk in depth about that today, but that if you're interested in that kind of thing, you can reach out to us and we'll help you set it up.
Cool. Thanks.
Cool. Lovely questions, guys. You guys are coming up with some great ones, and I love it. These are like perfect leading ones, giving us a little tour of all the things I won't be able to cover in depth today, so keep them coming. Um, one of the things we've tried to do with these cognitive service bindings is make them really easy to use. If you've ever used a service before, you know that there's just like a slew of doodads and knobs and dials you got to turn in order to get these things to work. And we try to make it as easy as possible to not have to deal with the full complexity of those knobs and dials if you don't need to. But if you need to, you have full control over the knobs and dials. So we'll give a few examples here. If you say want to do Bing image search and get results for multiple search terms, here you can make a data frame of queries and set the query parameter to look at a column called queries. So that's sort of a very simple usage, and setting up this Bing image search transformer is correspondingly simple. If you have a more complicated multi-tenant search application where you've now got to set the query, the offset, and a subscription key to be different for every single request, you can just fill those in with columns of the data frame. So you can now point the offset, basically which page of the Bing image search you're returning, or the key, which cognitive service you're actually calling. So you can set all these various different things with columns, or you can set them with a static value as well, so that you don't need to pollute your data frame with extra parameters. So there's kind of a wide variety of different ways to parameterize this. And the idea is that your parameterization complexity should scale with the complexity of the actual calls you're making. So if you want to do something really complicated, you'll be able to do this by putting the corresponding data in the data frame and sending it off to the service. And so now that I've kind of covered basically how to use the cognitive services, we'll talk a little bit about some of the special sauce underneath the hood that makes it performant and easy to use and things like this. The first key major operation that will make this a lot faster than you trying to roll it yourself in a UDF or map partitions is the introduction of asynchronous computation into the flow. So ordinarily, Apache Spark's parallelism model, it works by you have a Spark cluster and it's got a whole bunch of Spark workers. These are entire machines. Each worker has a bunch of threads, and these threads pick up work and they churn through them. But with web service computations, it's not quite like other computations in Spark, because a lot of the web service call is actually just waiting around for things to happen. You send data to some service, and the service does the heavy lifting, and you're left twiddling your thumbs. And so in order to really make sure that your cluster is not slacking off and is doing the most work possible, we've added this ability to, within a thread, perform asynchronous computation. So this means that you can send multiple requests while one request is percolating and getting computed by the server. So this allows you to get an extra order of magnitude of throughput for absolutely free, using the same workers on your cluster. And it helps us kind of perform a lot better than some of the other competitors. And this is in combination with some adaptive backoff strategies we have, as well as adaptive retries and adaptive throttling, so that you don't actually have to worry about whether or not your services can handle this. The cognitive services on Spark will really slow themselves down in order to play nicely with the services you're blasting with all the different data from your Spark cluster. Cool. So now that we've kind of seen how to use these cognitive services to directly solve your problem, what happens if we actually can't find a service to solve our problem? Like, what now? And so one of the main solutions to this problem is the Onyx um, deep learning and more general machine learning intermediate language, which effectively aims to take a wide variety of different machine learning ecosystems and be able to export them to a nice common language that can be run on accelerated hardware, that can be run really anywhere, on accelerators, on a large Spark cluster, on your mobile phone. And so what the Onyx community has done has built kind of adapters for a huge number of different ecosystems out there. And by supporting Onyx, we effectively support a wide variety of these ecosystems. So if someone out there has solved a problem, you can import this into Spark and deploy it at very large scales. And this is now, I should mention, not requiring the internet. This is your actual cluster doing the computation as opposed to a server doing the computation. And so what it kind of looks like here, I've shown it in Python just for a little bit of diversity, is that you can pass in the Onyx model here, set it to run on GPU, plumb it together with the columns of your data frame, and it automatically supports batching and things like this. And then you can execute this Onyx model on your large distributed cluster. This is due to the fantastic contributions of Jason Wang, who's done this and many other things around the library, just prolific. And I'll briefly call out this one line up here, the hub.load. What this is it's a model hub for the Onyx ecosystem that we've contributed back to Onyx as part of this work. And it will allow you to, in one line, download a whole bunch of Onyx models to your cluster. And this is currently supported in Python, and we'll be working on supporting this in .NET in the near future. And so with this, there's this 120 figure is a little bit old. There's now probably like 160, 170 different models in the Onyx Model Hub. So hopefully one of them can solve your problem. And what happens if you can't get one of these Onyx models or one of these services to solve your problem? Now we're going to enter into the phase of the talk that's about distributed model training. And there's a lot of things in the library that do distributed model training, but we'll cover the most popular aspect of model training that we've seen, which is LightGBM, a distributed gradient boosted tree framework that's GPU accelerated. It came out of Bing and Microsoft Research Asia. It's really efficient. It's super scalable. There's all sorts of sparse optimizations that have been honed over, decades of running Bing effectively. And it's incredibly high accuracy. It's often better than deep learning models, which is, surprising. I'm a gradient chauvinist for sure, but these gradient boosted trees are often better than deep learning models for tabular data. And so as a result, they're all over Kaggle. You'll see a lot of Kaggle winners will use LightGBM in their computations. And so that's kind of why we've decided to bring this into the Spark ecosystem to make this really easy to use on Spark. And so a bit of the details on what's going on under the hood is that ordinarily the most general thing Spark gives you is called map partitions, which allows you to just run arbitrary code on a chunk of data. And this is all well and good, but for LightGBM, we need to allow partitions to talk to each other. We can't just run isolated code on each worker and hope to fit a distributed tree model. It often requires like talking and all reducing these fit models in order to get a good model that's trained on a variety of different data from all the different partitions. So to do this, we actually use this new Spark barrier execution mode, which turns over control of the Spark cluster to you. And now you can orchestrate the distributed job. And so what we do is that we stop Spark in its tracks. We transfer it over to LightGBM. LightGBM does complicated peer-to-peer communication using these fast socket protocols. And once it's actually done doing this very large training job, it takes that trained model, it broadcasts it back out to the workers, and then we're back in regular Spark land where we can apply map partitions and just predict, evaluate on the data in each partition with naive parallelism. And so I'd like to call out the developer Ilya Matyach, who figured out this very delicate dance of kind of transitioning control over to LightGBM and using LightGBM's distributed computing framework to actually fit the model and then transferring it back to Spark. He's been with us about 5-6 years, total genius and the sweetest guy ever. Sweet. So now we're up to the final section of the talk, and hopefully we're still within time. And this section is kind of what in tarnation is the model doing? And to explain this part of the talk, I often like to start with a simpler problem than model explanation, which is called the jazz band problem. So say a singer, a drummer, and a pianist, they get together and they play a jazz show at a club, and together they make $1,000. So the natural question is, how should we pay these musicians fairly for their contributions? So the pianist says, well, how much would we make if we all played individually? So the singer would make $200 if they just sang in the jazz club. The pianist would make $300. And well, nobody wants to listen to just a drummer in a jazz club. You know, that's a different kind of club. So the drummer would kind of get royally screwed here based on their marginal contributions if they were just the only one playing. So the drummer doesn't really like this payout, doesn't really think that it's fair. And, you know, the drummer says, what if we looked at how much we would have lost if one of us was missing? And this is just as arbitrary. You know, it's just as arbitrary a computation. And so there's no real clear thing to figure out how we can actually pay these players fairly. And so, to understand what it means to pay players fairly, some mathematicians have come up with some really natural axioms to describe what it means to pay people fairly. You don't need to worry too much about the details here, but there's kind of four very simple rules. And the first one, efficiency, is that you pay people as much money as you received. So you split up the $1,000, nothing more, nothing less. The symmetry axiom says that if two people are identical, they should be paid the same. The dummy axiom, you're all probably familiar with this, says that you know, if you have a freeloader who does nothing in all circumstances, don't pay them. And the linearity axiom says that if you play the club today and you play the club tomorrow and nothing changes, you get paid the same. And what's surprising is that these four axioms that are very reasonable for how we should pay players fairly completely specify one unique way to pay players called the Shapley value. And this very particular game theoretic quantity is sort of the fair payout to all the players. And you can kind of compute this by looking at all the different ways you could have formed the jazz band, all the different orderings like singer, piano, drummer, singer, drummer, piano, looked at the marginal contributions of these players, and averaged them up over the entire ways you can have formed this jazz band. And this particular value is really nice because you know, in the context of jazz bands, it tells you a nice way to pay your players. But in the context of machine learning models, it tells you how to take your output probability and split it up amongst the input features in the only way that satisfies axiomatic fairness. So it allows you to take your probability and figure out which features corresponded to the prediction of your model. So in this particular case, we see that the dog's furriness was a really big predictor of the fact that this model spit out dog as the actual identification of this image. So you really get this fine-grained view of what's going on in your model through these Shapley values. And so one nice thing is that because these are the unique values, they've unified a whole bunch of things in the academic literature. So there's a whole variety of different, oh, my deck is lagging a little bit. There's a whole variety of different papers that this unifies, and I'll just put this up here for reference, and you can kind of read about it later. But what's nice is that all these different machine learning model explanation methods are implicitly approximating the Shapley value. It's in some sense one of the best ones, one of the unique ones for doing this kind of thing. So what we have is a really nice API for doing this on Spark, so that if you have a model that, say, does image classification, text classification, tabular classification, you can very quickly kind of use that model and understand what the model is looking at by passing in what your inputs are, what your model is, what your target column is. And if you fit this, you'll then get a really nice visualization of which pixels actually corresponded to your model's prediction. So in this case, we're trying to understand why this deep image network said that this was a violin. And what you find is that it perfectly highlights the pixels of the violin body. So not only can this help you debug your models, it can also allow you to pull blood from a stone and take classifiers and turn them into semantic segmentation models. And So really it allows you to take a really weak learning signal, aka tags or classes, like you just know that this is a violin, and turn it into something that's a fairly strong learning signal. You now know the exact pixels of the violin. So it's kind of magic in addition to telling you what your model is actually looking at and allowing you to debug your model at a high level. And this is another great contribution from Jason Wang. He built the Onyx integration. He built the SHAP integration. He built the OpenCV integration. I mean, the man's got fingers on fire here. And finally, I'll briefly mention that all of what you've seen here today is available in a wide variety of languages. So we support Python, R, Java and Scala, as well as .NET, C#, and F#. And so this particular contribution is new in the latest release of SynapseML and was contributed almost entirely by Serena Ron, who's just prolific in her ability to take on new challenges. She had never worked in the .NET ecosystem before this project and was able to kind of auto-generate code in .NET and contribute a lot of some of these contributions back to the core Spark.NET library in addition to our library. So shout out to her for really creating all of the content of this talk. So now that we've kind of seen some of the features of SynapseML, I can briefly describe some of the customer engagements. We might be running short on time, so I might skip the NASCAR one, but we can briefly talk about our customer engagement with the Metropolitan Museum of Art. This customer engagement really aimed to solve a problem that the Metropolitan Museum faced during COVID, where they had to close their doors and could no longer accept visitors. So they were really looking for ways to engage with visitors online so that anyone could enjoy the collection on the Metropolitan Museum of Art. And so what we did is we tried to design an algorithm that channeled inspiration from a particular exhibit at the Rijksmuseum in Amsterdam. And so what this exhibit did is that it's called Rembrandt and Velasquez, and it took works of art from the studio of Rembrandt and works of art from the studio of Velasquez, a famous Dutch and Spanish painter, respectively, and it put them in dialogue with each other. It kind of juxtaposed them together. And so even though these studios didn't really have any contact with each other, they were separated by thousands of miles and hundreds of years and things like this, they still kind of painted in similar themes and similar forms that could be combined and compared and contrasted. And so here you kind of see the martyrdom of Saint Serapion, and he's holding his arms outstretched, sacrificing himself for the sins of the world. And on the right, you have the threatened swan, and this swan has her wings outstretched and defending her nest from this dog over here in the lower left corner. So even though these painters never talk to each other, they still make these paintings that have very similar forms and even mean very similar things if you think about them symbolically. So what we tried to do is create an algorithm to find these very uncanny pairs of artworks automatically so that you can discover hidden connections within the corpus of art. So what we did is that we first built a deep image retrieval algorithm by taking images, passing them through deep convolutional networks to get good features, and then looking them up in the collection of the Metropolitan Museum of Art with a fast nearest neighbor lookup, so that you can kind of take an image and find the closest match in the Metropolitan Museum of Art. This allows you to sort of take your Instagram feed and metropolitanize it. This isn't quite what we wanted for our particular application. In particular, we had to change up the nearest neighbor lookup to give you the closest match, but conditioned on, say, it being Rembrandt or being from Velasquez's studio. So this allowed us to find the closest image with these various different conditioning filters, like the closest painting, the closest ceramic, the closest Japanese artwork, the closest work from Rembrandt, the closest work from Velasquez. And now this gave us the kinds of queries that could support the algorithm that we saw before. So now we can take an image from the Metropolitan Museum of Art and find the closest musical instrument, the closest woodwork, the closest weapon, the closest thing in the Egyptian collection. And these kind of rediscover these uncanny pairs. You take a blue and white floral garment and you find a beautiful blue and white porcelain violin. And this not only just looks the same, they're actually kind of channeling the same artistic influence from Ming Dynasty porcelain back in China. So it kind of serves a similar purpose, where we found these works of art that are uncannily similar and also speak to some core semantic similarity in the works of art that humans have produced over time. And you can, I'll skip the architecture here, but we built this kind of thing with SynapseML, and you can play with this live online today. We have this website, aka.ms/mosaic, where you can really explore the collection, try it out, try to find these conditional matches, of course, a variety of different starting images, cultures, media, etc. So hopefully you find something fun in there and enjoy the millions of works of art in the Metropolitan Museum of Art collection. And yeah, I think that we're probably closing in on time here. So I'll maybe only briefly talk about our work with Hendrick Motorsports. So in particular, Hendrick Motorsports is a NASCAR racing company. They sponsor a team that has esteemed racers like Jimmy Johnson, and they try to race around the track really, really fast, try to get the first person to complete like 300 laps on one of these oval tracks. And a lot of people are really excited about it, and the Hendrick Motorsports team is really looking for that edge. They really want to win this. So what NASCAR gives them is live telemetry from all the 60 different cars that are going around these 300 laps, and driver audio from every single one of these cars. So what we do in SynapseML is we pump this driver telemetry through the anomaly detector and write it out to an Azure search index. And we also take the driver audio and run conversation transcription on it, so that we know who's saying what at every single point in the race, and also pump that into Azure Search. And what we get is kind of on top of this Azure Search cluster, we can build out a live racing dashboard that can give key insights into the race. So here's one particular view of the anomaly detection that came out of this kind of system, and you can kind of see this is the RPM for car number 32. In a variety of different places, there's red here, and most of these red locations are areas where someone's crashed on the track, that someone slammed into a wall or whatever, and everyone needs to slow down while they clean it up. And you can see this kind of final anomaly detection result here is there's a lot of red, and it never kind of recovers. It never goes back to its normal behavior. And this is because this particular moment, car number 32 is slamming into the sidewall and, had to be taken out of the race. And thankfully, the driver is okay. But these kinds of things, even without knowledge of the structure of a NASCAR race, these cognitive service anomaly detector can pick up on key structure of the race that's important. And with the conversation transcription, you can kind of figure out what different teams are doing in the race in real time. So a lot of these teams, they'll speak in code words so that they don't tip off other teams. And what Hendrick has been able to do now is figure out those code words, so they can figure out what all their competitors are talking about in real time and search it up so that they can kind of better attune their strategy during the race. And so, yeah, thanks for listening. And I'll briefly end with a call out to the new version of SynapseML. This version we just released a few days ago, and it's got support for OpenAI language models, these 100 billion parameter language models that are really scarily sentient. You can complete text, you can solve a variety of different natural language problems just by prompting these algorithms with various different prompts. If you wanted to do translation, you give it a few examples and ask for a completion, and it will translate your text. You want to do named entity recognition, you give a few examples of inputs and outputs, and boom, it'll serve as an entity detector. So it's really interesting. You can kind of construct whole models just by prompting this thing. This is the release that has full support for .NET, C# and F#. So please definitely give it a try. Let us know what you think. Let us know how it's working for you, and let us know how you use it. It's got support for Binder, so you can try this live in browser without even having a Spark cluster. And it's got full support for MLflow. So if you use MLflow, you can now SynapseML and SparkML is fully compatible with auto logging, saving, loading, serialization, etc. And with that, big thanks to Serena, who built out these bindings, as well as to the rest of the Spark.NET team. and Eureka especially for doing all of the code reviews and things like this. And thanks as well to the other contributors of SynapseML who made this talk possible. And thanks to you all for listening. And even though we went a little bit over, really appreciate your patience and time. So.
No, not at all. I think that this was really great. We still have a few minutes left here. So I'll just make I guess, a final call for folks if there's any questions or anything they'd like to comment on, to post it into the chat. And yeah, I guess question here is Mark Hamilton your real name?
No, it is. It is. Yeah, no, I don't know if this is in reference to Mark Hamill, but yeah, I mean, I've
Yeah.
completed his name.
Gotcha. Yeah, I mean, for me, right, like I think that this is just a really fascinating addition, right, to sort of the .NET ecosystem. So for me personally, I would say that if you are a somebody who's working with Spark already, right, and you do have those sort of needs for machine learning, and you're mainly a .NET developer, I think that this is a really really great sort of addition to your tool set. And there's a lot that you can do here. So I'm really excited for this work, and sort of the work that you guys are all doing there. I think you mentioned Onyx was one of the things that's sort of coming in the near future. What else is next for SynapseML?
Yeah, no, that's a great question. So, some of the things we have slated are to take our R bindings and get them to the full GA support, kind of meet parity of our Python and .NET bindings. So that's kind of one thing coming up. In addition, we have a few really nice deep learning APIs so that you can do not just deep learning inference, but deep learning training and solve a variety of simple problems. And so that's another nice contribution that's coming up. And we'll hopefully do kind of some of the things like bring in the Onyx Model Hub to .NET, and figure out, now that we're in the .NET ecosystem, there's a huge amount of great IP out there like ML.NET and others. And I think one of the things that we still have to tackle is to figure out how we can really work with this community and leverage its strengths. So, perhaps this is an open call to the community. If you are a .NET lover who wants to contribute or has ideas on things that we can do to integrate with your particular libraries and communities of choice, definitely drop us a line and let us know.
Yeah, and as you make these updates or anything else, right, these contributions come from the community. We'd love to have you back on, right, to showcase sort of those new features. So yeah, the invite is open, and we'd love to have you again. We did have a question a while back, and this kind of I think is in relation to it being 0.10. Sorry, I'm just trying to find it here. But basically, like the question was, and I'm paraphrasing here, is it production ready?
Yeah, no, that's a great question. So even though it's 0.10, we do have GA support for it on Synapse Analytics, so general availability support. So this means that if you use SynapseML on Synapse Analytics, you can write us file an issue on us if there's a bug. You can contact us if there's any issues, and we'll gladly help you out and help you make sure that your pipeline succeeds. And we'll be releasing 1.0 shortly. And really why we chose to keep it on 0 is so that we can clean up the APIs a little bit more, like remove any cruft from the library before our big 1.0 drop. So stay tuned. And if you use any of the things we've talked about here today, there's not going to be much API changes.
Great. Awesome. So I don't see any more questions, and we are almost at time. Again, I just want to thank you, Mark, for coming on and sharing some of the work that the team is doing, and really engaging the .NET community. I'm super excited to see what's next for SynapseML, as I'm sure all the folks who joined today are. So yeah, definitely go try it out. I believe to get started, the blog post that you released that has a few instructions on how to get started. Is that right, Mark?
Yep.
Okay.
Yeah, so you can check out that blog post. Our website will have similar instructions. And thank you, Luis, for really hosting this and giving us this amazing opportunity to share with the .NET community. We on the SynapseML team are super appreciative of the work that you guys do and in organizing this great community.
Yep, absolutely. Yeah, happy to have you. All right, folks. Well, that brings us to the end, and we will see you next time on the Machine Learning Community Stand Up. Thanks, everyone. Take care.